Okay, so in this chapter we'll talk about sources of magnetic fields. Okay, what produce magnetic fields? And so we'll talk about this. This is a pretty cool toy. We'll get to that in a second. Okay, so this chapter is about sources of magnetic fields, and again, like we said, the Maxwell's equations describe all classical electromagnetic phenomenon. Okay, these are the Maxwell's equations in differential equation form. Here are the Maxwell's equation in the same thing in integral equation forms. Okay. Again, these are the sources on the right. The left-hand side is the effects. Okay. Charges produce electric fields. What this says is time-varying magnetic fields produce electric fields. Okay, right now, so to give you a sense, this is how all electricity is produced. Okay, this equation is the basis for all electricity. Okay, there's trillions of dollars invested in this. Dams produce like this, windmills produce like that, electricity like that, and we'll learn about this next chapter, or soon anyway. The only thing that does not produce electricity using this equation is photovoltaic cells. Okay, but anyway, that's okay. So what produces magnetic fields? This equation tells you that. Moving charges and time-varying electric fields produce magnetic fields. We'll talk about this half. So we'll talk about moving charges producing magnetic fields. All right, so that's what this chapter is about. Okay, again, half the equation. All right, so here are so this is the basic law. We'll study Biot-Savart law, okay? And then we'll study some other stuff, okay? So here's what is called a magnetic gun, okay? And this is at a Sandia National Lab in Albuquerque, New Mexico. So here's what it can do. Shows a projectile can be launched. This projectile, whatever projectile was launched at 3 kilometers a second. Okay. And see, over a very small length, it went from 0 to 3 kilometers a second. The acceleration, so here's another instance, the accelerations of 5 times 10 to the 6 G's were imparted on this object for about 1 millisecond with a launch speed of 10 kilometers per second have been achieved. All right, so okay. So the acceleration of this guy was...
That's what a railgun is, right?
Yeah, that's a railgun. Mm-hmm. This acceleration, what does that mean? That means the force on this object was 5 million times its weight. Okay. So for instance, if you launched your physics professor there, what you would get out is a pellet. Did you guys understand that? You apply a force of 5 million times the weight of this object on this object, it gets squished. So you could only launch solid objects this way. Okay. Do you guys remember what is the escape velocity from Earth? 11.2 kilometers a second. Okay, so this is essentially giving an object escape velocity. Of course, the drag will slow it down, but you can launch using this gun, which is the size of this room, maybe a large room, and you can launch stuff into space. Okay, so how does this work? Okay, so here's the rail part of the rail gun. Okay, so here's a metal rail, and there's a conducting fuse. Okay, and when you want to fire something, all you do is close a switch, pass a current through here. So this is a rail, so a conducting rail, here's a current that'll pass through. And this is a conducting fuse, current will pass through there. And it's a fuse, so as soon as the current passes, it heats it up and it melts it. It makes it a plasma, essentially. Okay. So here's a top view, here's the current. So the current is positive charges moving in this direction, and you have a magnetic field between the rails into the sheet. Okay, V cross B. So V cross B, so here's V and B is into the plane. V cross B will give you a force in that direction. So that magnetic field exerts a force on all the positive charges in that direction, and that pushes the payload. Okay, and so within, let's say, 10 to 20 meters, it's giving it an acceleration. Well, it's giving it an acceleration of 5 million Gs. You saw that. That thing goes from 0 to 10 kilometers a second in a millisecond. Okay. Now that's a big boy toy. All right. All right. Again, so in this chapter, what we are studying is what produces magnetic fields, and moving charges are producing magnetic fields. So we'll finally learn the precise nature. Okay. And one of the later chapters will study time-varying electric fields producing magnetic fields. Okay. All right, so here is the field. Okay, so you take a proton or a positively charged particle, and when it's moving, so it produces an electric field, but right now we're concerned with only the magnetic fields. So when it's moving in this direction, now what you do is, so you draw a cylinder. Okay, so let's say, so I'm going to draw this. And if you have a positive charge moving along the axis, the magnetic field is tangent to the cylinders. Okay. And further out you are, so bigger the cylinder. For a bigger cylinder, the field, of course, gets weaker. Okay. So point your thumb with your right hand, point your thumb in the direction of the motion of the charge, and your fingers point in the direction of the fields. Okay. So that's what this is saying. Okay. So this charge produces this field. Okay. How far out does it produce a field? All the way to infinity. Okay. Now we're not. So what we are giving you is a picture of you had an infinite stream of particles going in that direction, because quantum mechanically, when it's here, it produces a field that travels at the speed of light from it. Okay, but we won't worry about all those complications. Right? What this diagram is showing you is, so if the positive charge was going into the sheet of the paper, that's the sense of the fields, magnetic fields. Okay, again, point your thumb into the paper, and your fingers point in the direction of the field. Okay, so at this point the field is like that. At this point the field is like this. Okay, and the further out you are, the weaker the field gets. Okay. All right, now we'll give you a precise expression for this field. Okay, and there is the field, and this is known as the Biot-Savart law. Okay, so here's the charge on the particle, here's the velocity of the particle, cross r hat. So here's the particle, and here's r hat as a unit vector pointing toward the point at which you're trying to find the field. Okay, r cross v, v cross r hat, v cross r hat. When you turn a screw from here to there, it points in this direction. Okay, so that's the direction of the magnetic field. This gives you the direction of the magnetic field. And the field strength drops off as r squared. So r is this distance. So the further out you are, the weaker the field gets. Okay. Now, what this is saying is along the axis, so along points in the direction of the field is zero. So this charge produces no field there. That's because V cross R hat is zero. And it produces no field there. That's zero, okay? So along the direction of motion, that's along that line. On that line, the field is zero. Everywhere else, it's non-zero, okay? Did you guys understand that? Okay, so there's the punchline of this chapter, okay? Moving charges producing magnetic fields. So if it's not charged, it's not producing a magnetic field. If it's at rest, it won't produce a magnetic field. And the magnetic field falls off as 1 over r squared. Mu naught is a constant. It's called vacuum permeability. And that's its value, okay? So, all right, do you guys understand that? Okay, so again, stick your thumb out in the direction of motion of a charged particle, and your fingers point in the direction of the magnetic field. Further out you are, weaker the field, and so on. Okay, so can anybody tell me if this was a negative charge moving in this direction, which direction would be the fields? In the opposite direction. If Q was negative, the magnetic field would be in the opposite direction. Okay? All right, so moving charges produce magnetic fields. Now let's build on that. Okay, now let's say you have a current carrying conductor. What is a current? It's a bunch of charges moving. Each charge produces a magnetic field. So let's say this is a current. It's a whole bunch of positive charges moving that way. Each charge is producing a magnetic field coming out of the plane. And so a whole bunch of charges moving, all their fields would add up. Yeah. So current carrying conductor would produce a magnetic field as well. And the field due to the charges contained in this length of the wire is given by that expression. Okay. So again, mu naught over 4 pi, the same factor. Okay. And there's the bunch of charges moving with velocity. Okay, so the current is related to the velocity, and the length tells you, the length of the wire tells you how many, along with this thing tells you how many charges are moving. So the field due to this length of the conductor carrying that current is given by that. All right. All right, so what if you wanted to calculate the field at this point? Again, r hat is unit vector from this piece of the conductor to that point. So if you wanted to find the electric field, the magnetic field at this point due to this wire carrying a current I, you just have to do this integral. So you're summing over all of those ds cross r hats. Okay, so here it is ds cross r hat. At this point, this would be ds, r hat would be there, okay, and so on. You're summing over all of them. Now this integral, in general, if you had a wire like this, for instance, and wanted to calculate the field at that point, that would be impossible to do. You can do this integral for very simple cases. If you had an infinitely long straight wire, it can't have any kinks or anything. So if you had an infinitely long straight wire, that integral, it's possible to do that integral. Okay? So for an infinitely long straight wire, you can calculate the magnetic field at this point. And again, what is the direction of the field? So for a current passing through there, again, stick your right hand out, point your right hand, the thumb in the direction of the current, and your fingers point in the direction of the field. So the magnetic field will come out of the plane of the paper. Yeah. So again, somebody's done this integral for you for an infinitely long straight wire. You can't do the integral for a wire like this. Okay? And here's the answer. So for an infinitely long straight wire, the magnetic field at this point is pointing like that. It's tangent to the circle. Okay? And the strength of the magnetic field is mu naught, that constant, times the current divided by 2 pi a. A is the distance from the wire. Okay. So here is a current producing a magnetic field. Okay. And that's this part of the equation. Okay, so that's what we are studying. Currents producing magnetic fields. Okay, and so what we have done is we've shown you for the simplest configuration a calculation expression for the magnetic field. Okay? For an infinitely long straight conductor current, B is mu naught I times A, 2 pi over A. Now you see that if I is 0, the magnetic field is 0. If you have no current, you have no magnetic field. Okay? Everybody understand? Okay. All right. Now we'll look at the next interesting case. So now we saw the magnetic field produced by a long straight wire. Now here's another interesting case, a ring carrying a current. Okay, so of course you could do that. So here's how you could. So here's a switch, and there would be a break. Oops. So current is flowing through like this and coming back like that. So there's a break in the ring. So you could do something like this. Okay, so if you have a loop of wire carrying a current like that, it produces magnetic fields like this. Okay. Now, what's interesting about this is, see, this magnetic field is exactly similar to the magnetic field of a bar magnet. Okay. Now, we can't give you the expression for the strength of the magnetic field. If you ask me what is the magnetic field there, I can't give you an expression related to I. That's too complicated. Okay, it's hard to calculate that. But what's interesting is this field is very similar to that field. And this is called an electromagnet. And as we already mentioned, when you want to turn off the magnet, you just open the switch. When you want the magnet on, you close the switch. Okay? So this is an electromagnet. Okay? And that's very useful to us in our lives. Yeah. This magnet, you can't turn it off. And not only that, you can't change the strength of this magnet. But this magnet you can turn on and off, and you can change its strength as needed. Okay? All you have to do is change the amount, okay, the current passing through there, and you want to make a stronger magnet, you just pass a larger current through it. Yep. So this device is very useful. All right, so if you had this loop, and the radius of the loop was r, what we can do is, we can't give you an expression for the magnetic field there, but we can give you an expression for a magnetic field along the axis. Okay, if you are along the axis, so let's say there, r is this radius, and z is this point. So along axial points, the magnetic field is given by that. You guys, we've already talked about a current carrying loop is a magnet, and the strength of the magnet is mu. The magnetic moment is mu. And do you guys remember the expression for the magnetic moment? N times I times area. What is N? The number of loops in the wire. I is the current, and A is the area of the loop. Okay, so the strength of this magnet given by the magnetic moment is that. Okay, that's mu there. So what is this expression? This is the magnetic field along axial points. If you're slightly off axis, we don't have an expression for that. Okay? I'm sorry?
I meant my stomach, sorry.
Oh, I see. Are you hungry? All right. As long as you're not sick, my friend.
It's just making my water boil.
Yeah. You guys understand? Okay. So what this expression is giving you is, what this graph is showing you is if you had a, oops. So let's say you had a loop of wire like this, and X is in this direction. So carrying a current. Okay. So what is the magnetic field? Remember, we can only give you expression for magnetic fields along the axial point. Okay. If X is this distance, and this has to be large compared to the radius of the loop. Okay. So for large distances, there's the magnetic field. Okay. Magnetic field is mu naught divided by 2 pi. Mu is the strength of the magnet. Okay. Mu is again N times I times area. Okay. And the magnetic field falls off as X cubed. Okay. That's what it's saying. Okay. And mu is the strength of the magnet, which is N times I times A. All right, now I want you to understand this part and then we'll stop. Okay. For today. All right, what have we learned? What produce magnetic fields? I'm sorry? Moving charges. And currents are composed of moving charges. So if you have a current carrying conductor, that'll produce a magnetic field. Do magnetic fields have effect on other moving charges? You guys remember this expression? F is QV cross B. Okay. So if you have a magnetic field, the only way to detect a magnetic field is use another moving charge. Okay. So if you have a moving charge in the presence of a magnetic field, it feels a force. All right, so let's see what we'll do is we'll take two wires. Okay, we'll pass currents through both the wires. Okay, this is a bunch of moving charges. This is a bunch of moving charges. These moving charges produce a magnetic field. Okay, so you can think of an infinitely large wire. Okay, stick your right hand, your thumb of the right hand like this, and this will produce magnetic fields like this. So this wire will produce a magnetic field in this direction at this location. And if this guy is carrying a bunch of, this guy is carrying current, that's a bunch of moving charges. So that is a positive charge moving in this direction. All right, this current produced this magnetic field, and these charges are feeling this magnetic field. Okay. So V cross B, it feels a force in this direction. So all these charges feel a force in that direction. Okay, so we argued through all the details. Now let's look at it from another perspective, or a simpler perspective. So it seems like two wires carrying currents in the same direction will attract each other. You can do the same thing for this guy, and you'll find that the force on this guy is that way. Okay, so parallel wires carrying currents in the same direction will attract each other. And you can figure this out. If the currents are in the opposite direction, they'll repel each other. Okay, so parallel currents attract each other, and anti-parallel currents repel each other. All right, so if these wires are infinitely long and so on, the force per unit length on the wire of these wires is mu naught I1 I2 divided by 2 pi a. A is the distance between the wires. Okay, so let's say this I is 10 amps and this is 0 amps. What is the force between them? I'm sorry? I'm sorry? Let's say if one of them is 10 amps and this is 0, what would be the force between them? Yeah, so one is 10 amps, one is 0. The force would be 0. Okay, so both of them have to carry currents to have a force. Okay, again, parallel currents attract each other and anti-parallel currents repel each other. Okay.
Do the magnetic fields interact? So like if you have one going one way and one current going the other way, then do they cancel out at certain points?
Yeah. Mm-hmm. Yep. Yeah. Okay. So you can have the currents going in the same direction and they can cancel out. So this guy will produce a magnetic field like that. Let's see. This guy will produce a magnetic field like that. This guy will produce. So you can have cancellations in between the two wires. So you can have a cancellation along a line, and the line distance will depend on if this current is higher, the line will be closer to that guy. Okay. So you can have cancellation along a line for infinitely long wires. All right. Okay. So remember this, parallel wires will attract each other and anti-parallel currents will repel each other. All right. So here's the fundamental law. And this is the Biot-Savart law in terms of the currents. Okay, what this tells you is if you had a wire, arbitrarily shaped wire, and you wanted to find the current and the magnetic field at this point, you would do this integral. Okay, so let's say here's the shape of the wire. Okay, and this is carrying a current I in the wire. You wanted to find the magnetic field at this point, you would break this wire up into little pieces, calculate the magnetic field due to this guy, and that's what this is, times mu naught I, and then sum over all the little pieces, and that's the integral. All right. What if I had another wire carrying, this is I1, I2, and I wanted to find the net field there. Okay, so you would do the integral for each one and then do the integral for other and add up the vectors. Okay. Again, those integrals are not easy to do. Okay. So remember, for charges, you could calculate the electric field due to this charge, which was kq over r squared. What if you had another charge, q1, q2, e1, e2, you calculate the field due to that guy and so on, okay? So to make things life easy to calculate electric fields in symmetric situations, you had something called Gauss's law. Gauss's law gave you the flux through a closed surface, which was equal to E dot dA. Okay, this is an enclosed surface, was equal to charge inside divided by epsilon naught. This was Gauss's law. The parallel of this law is what we're going to talk about. Okay. So, and the parallel of that is called Ampere's law. Okay. So if you had multiple wires carrying currents, each of those wires is producing a magnetic field at this point. Okay. Each of those wires is producing a magnetic field at every point. And the net field is just the sum of all those fields. Okay? And so Mr. Ampere summarized all of that. And so what he says is, if you can draw any curve in space and take the line integral of the magnetic field around that curve, and that will equal mu naught, that's a constant, times the total current threading that loop. Okay? And again, the sign convention is as follows. You use your right hand. If you go around the loop in this direction, positive direction for the current are like that. So you use your right hand, and if your fingers point in this direction, so that's the direction in which you go for the line integral, your thumb points in the direction of positive currents. Yep. So this line integral for a closed loop is equal to mu naught times I. I is the total current threading that loop. So let's see if you understood that. So let's say I take a loop like this. What is the line integral around that loop? 0. Okay. What will be the value of the line integral around that loop? You would sum all those currents. Okay, and so on. So this is Ampere's law. Okay, and again, this is useful only in very symmetric cases. Okay, so for instance, you could use Ampere's law in this situation. Ampere's law is easier to use in this situation rather than this law, rather than doing this integral. Okay, this integral would be much harder than using Ampere's law. Okay, so just like that, just like Gauss's law allows you to calculate electric fields in symmetric cases, Ampere's law allows you to calculate magnetic fields in case of symmetric currents. Okay. All right. So again, you can do the line integrals about various curves, and so you already answered this question. If you did the line integral around that loop, you'd get 0. Okay. So we will stop here today, and I'll continue